Everyone, this is theory topic J, testing. Before we get started, just want to draw attention to a couple of other things that are added to the assignment. The first of these is this, which is a set of class notes. So essentially what I'd like you to do is to watch this video, and as it's going, you need to answer these questions, okay? So you'll probably have to print a copy of this out if I've not already printed one for you. There is an assignment as well that needs to get done at the end just to see how much everything is stuck, and of course obviously you've got the original presentation if you need it, which has got all the embedded videos in that should work. So let's get going on the topic of testing. Okay, so remember, as with all these units, this is the key sort of info that you need to be able to recite back to me. Okay, so if you get a question in your exam on your reflection about testing, I would expect you to show that you are aware of the different tests that are available to identify characteristics and properties of materials, and I would also expect you to display an understanding of how product testing is used in industry. Okay, so that is all that you're looking for in testing. Okay, the types of tests that are used and some specific understanding of how product testing is used in industry. So ultimately, we're going to start this presentation off by looking at what a well-designed product is expected to do, and that is to function efficiently. Okay, it needs to do everything that it said in its specification. It needs to work. It needs to work well. So if you take a second now, think, what's the one single thing that a car seat should do? Hopefully you said protect the baby during a car crash. It is. If you had to say one thing, that would be the one thing that it has to do. Now, how it does that is up to the design of it. It could, but the most important thing is that it protects the baby from an impact, whether that comes from the side or whether that comes from a head-on crash. And the point we're trying to make here is that manufacturers will go to some quite considerable lengths to test out their products, very often exceeding what is required. So for example, that car seat test there, that might withstand a car crash at like sort of 150 miles an hour and something heavier than a car going into it, because it needs to be absolutely sort of super safe. Likewise, if they were testing something simple like a chair out, they might want to test it to withstand 5 times the amount of weight which they actually want, just to make sure that there's absolutely no chance of a product failing. Now, when you're testing in industry, there's a couple of different ways that you would test. You'd probably test before the actual product is made by checking out the properties of different materials to see whether or not they're suitable. Whereas the actual product itself, you'd have to test that afterwards to try and sort of mimic some of the situations and environments that it would be in. So the first thing we're going to look at are some of the what we call mechanical tests that you apply to materials to find out certain properties. Those properties are to do with whether a material is tensile. So in other words, how does that material stretch and withstand sort of pulling forces? You also want to look at the hardness of a material. So in other words, how much sort of durability it would have. Looking at the impact, so whether or not the material can withstand a very specific impact. You also might want to consider abrasion. So that's like the everyday sort of wear and tear and durability going on for it. Now, because the material that you test would get damaged when you try these out, these are what we call destructive tests. Okay, so all these tests to determine tensile, hardness, impact, or abrasion are what we call destructive tests. However, some materials or some products you cannot test them in this way. They may have hidden things inside that you can't tell, stuff that's you can't tell it's wrong until you've actually finished the product. To do that, you might use things called X-rays, you might use ultrasonics, you might even use a device called a scleroscope, which we'll look at later. But these are all what we call non-destructive tests. These tests do not damage the material or the product in any way.
This is such a bad. Hold on, let me get from behind here so I can see everything. Okay. Hold on, this is really.
You're just gonna make it worse.
No, it's fine right now. That is the plexiglass that we're going to be using for this bad boy. And Gus is shooting at Ed's crotch. Oh, God!
Okay, so sometimes when you test a material, all you can do is damage it, but you need to be able to record exactly how much it's been able to withstand. So the first one we said we're going to look at is tensile testing, so how well a material stretches. You do this using a thing called a tensometer. Now what a tensometer does is it clamps the material in between two clamps, and then a worm gear actually sort of unscrews and pushes these two parts of the clamps away from each other, so it pulls the material out. So although it's not super clear on this video, these are actually moving further apart, and if you look in the middle you'll start to see when the material will start to stretch. There it goes. So obviously what it hasn't done is it's not stretched like a piece of chewing gum. So that's not a very tensile bit of material which they were testing. And as it's doing that, okay, so if I just dial that back a little bit, as this is pulling, there are sort of measuring devices which are seeing how this is being stretched. So it's plotting a graph where it sort of reaches a point where it kind of sort of calms down a bit, and then it very rapidly goes downhill, and then it fractures off there. All right, so they can use that to see the kind of strains and stresses on that particular material. A specific test for hardness is something called the Brinell test. All right, what the Brinell test does is it takes a tensometer but works the opposite way. It actually sort of pushes something into the material. In this case, it's a small ball bearing, a small stainless steel ball bearing. And when you push that into material, it's going to create a little dint, yeah? And what they do is you measure that dint, you can apply some sort of formula to it, and it'll give you a measure of hardness, okay? And we can see that on this clip here. Okay, so you push that into the material, and hey presto, you're left with a little dint there which you can work out. However, if you've got a really hard material, you can't push that little ball bearing into it. Okay, if you're testing a piece of stainless steel, if you push a stainless steel ball bearing into a piece of stainless steel, it'll do nothing. So this is where you need to do something called a Vickers hardness test. A Vickers hardness test, okay, is used for very hard materials, and a pyramid-shaped, diamond-tipped device is used to push into it. And again, it pushes in, it leaves a particular shape. However, the only way you can check this is with a microscope. The hole that it leaves is so tiny, you can only check it under a microscope. If you're testing a material's ability to withstand an impact, so that's a sudden sort of sharp sort of shock, strike to it, you do something called an IZOD impact test. Okay. Now what happens with an impact test is you take a notched piece of the material. So in other words, you take a little bit out of it and you hold it in a vise. You can see there the little where the notch is. And basically the arm of this machine is just like a pendulum. Okay, so the pendulum is released from a set height. It swings down through the material and actually snaps the material in two, and then it carries on traveling. So if you've got a material that will withstand toughness, that will withstand this impact, it will hit it, a lot of that impact will get absorbed, and then the pendulum will carry on swinging a little way. If you've got something that is not very tough, then it will swing through and it'll swing higher, all right, and it just records these gauges, all right, and you can see that on this video here. So there's the pendulum going up. They're setting that little device there to see, setting it to 0. They put the material in, bang, it swings up, and you saw there that little arrow. Yeah, it just got moved around to a certain level. So they're testing individual pieces of material. So yeah, she sets it, watch that arrow, bang, there it goes round to there. Yeah, so they might be doing that on a range of material just to see how well it's being produced. So there are some other impact tests. I'll run this video for a little bit. They basically work on the same sort of principles as the ones that you've seen.
resistance is one of the most important properties for a designer to incorporate and one of the most difficult to quantify. Instrumented impact tests record the entire impact event so that the full impact force versus time profile can be analyzed. In this particular ASTM D256 test, we're using a specimen of specific geometry. The specimen is held in a fixture and impacted through failure. With an instrumented TUP or striker, the impact velocity is recorded with an electric eye.
So this still works on the same principle of the IZOD test that we saw before, and you saw at the bottom it's still called an IZOD test. Okay, but you can see how it's also carefully sort of computer monitored in terms of measuring that particular impact. Okay, so we've looked at tensile and hardness and impact. Another test you want to consider is a test for abrasion. Now, there are certain British standard tests, and we'll look at British standards in a little while for testing for abrasion. So if we look at this one, you can see samples of material here, and then we've got this device which just rotates round and round, and there'll be some like sort of sandpaper material on here, so it's just wearing away, all right, to see whether or not a material can withstand a regular amount of abrasion. In other words, how durable it is as a material. Another method for testing out fabrics is this device here, which kind of wraps it around a drum, and then you can see this sort of medieval looking sort of ball here bouncing up and down. All right, just another way of checking sort of ongoing abrasion to a particular piece of material. Like I say, these are all part of British standards tests. So if you've got a piece of material which has sort of met a certain standard, it's because the material's been subjected to these tests, so you know it's quite stringent. If you're testing something like food, it's a little difficult though. You need to test food in a completely stimulus-free environment, so whether that's a blindfold, a dark room, with no sort of sounds, no smells to interfere with it. And how you'd measure it though is you kind of measure like certain qualities on a scale. So this is sometimes called like a sort of a star graph. It uses sort of pentagrams, and if you think of each level of these being like a sort of a 1, 2, 3, 4, so in terms, if this was testing a cake, someone might think that in terms of moistness for the cake, that it's a 4 out of 4. And same for airy, it might be full of lots of nice air bubbles, so 4 out of 4 for airiness. However, the sweetness is only getting maybe a 1.5, 2 for sweetness, and its richness is just about a 1. So these could be bits that you could actually sort of expand on and try and improve upon. If we go back to British standards, there's a video which you can watch, which is embedded, which gives you a lot more information about British standards. First thing, obviously, you want to dwell on here is this thing called the kite mark. If you've ever come across that, so if you see an item that has passed a specific British standard, it will have this logo on it and the numbers of the standard which it has passed on. It's a bit different to this one, which is the CE mark, which is like a European equivalent. But I use the word equivalent very loosely. European standards are nowhere near as strict as the British standards. So if you do see a product that's got CE on, yes, it's met a certain kind of standard, but it's nowhere near as good as one that's passed a British standard.
The BSI kite mark can trace its origins back to 1903. The forerunner of today's much respected and widely recognised kite mark was an ordinary trademark for tramway rails. In itself, this does not sound particularly momentous. However, standardisation of tramway rails helped to reduce the number of rail sizes from 75 to only 5, and in the process was estimated to have saved the industry the huge sum of £1 million. Today it is hard to imagine a world without agreed standards and specifications for performance, but without the British Standards Institution and the BSI kite mark, much of what we take for granted today would not have been possible. For 100 years, the BSI kite mark has been a uniquely powerful symbol of trustworthiness, recognised by engineers, industrial buyers, and consumers in the UK and around the world. The kite mark has become synonymous with quality and become interlinked with the economic successes of the last 100 years. The origins of BSI can be traced back to 1901. Central to the development of standards in the UK, and subsequently BSI and the kite mark, was one Sir John Wolfe Barry. Sir John was convinced of the need for standards in iron and steel production, and in 1901 set up a standardisation committee at the British Iron and Steel Association, with the aim of agreeing standards for iron and steel sections. The first British standard for steel sections was published in 1903 and remained virtually unaltered for 20 years. Having established the need for standardisation at the turn of the century, progress was steady up to the First World War. The war provided a major stimulus to the standards movement, and by 1920 there were 300 committees engaged in standardisation work, as compared with only about 60 before the war. The Second World War also saw a rapid growth in standardisation activity and the publication of a range of emergency standards.
Okay, so the general gist of that video, the key points you need to take from it really is the fact that it was initially sort of set up. I mean, the example they used was the tram lines. So in cities all over the UK, tram lines were actually different. So as a tram manufacturer, you couldn't guarantee that if you made it, it would work on them. You'd have to go out and measure them. So the British standard was set up to make sure that all tram lines were the same width. Interesting as well how it pointed out how standards increased during periods of war, when obviously the country was really sort of mass producing certain items that needed to be of a particular standard. Especially when you think of things like weaponry and bullets, stuff like that, you need to make sure that your bullets work in a range of guns, and that's why Britain did so well with things like that. Okay, so on to the second half now, which is looking at non-destructive testing. So, for example, if you've got a large casting, so if you look at this giant propeller here on the back of probably like a shipping sort of container type ship, that's a casting, like a solid sort of casting. There may be defects within there which you can't actually spot. So there's no, you would not on this sort of one-off sort of product put it on a boat and then put it on a ship and hope that it'll work. You need to sort of check. You need to be able to see inside it. You need to have like X-ray vision. And there are a few methods that are used, and we're going to look at the three main ones, okay? And that's ultrasonic, sometimes just called UT or U testing, magnetic particle testing or MP testing, and a liquid penetrant test or LP testing. All right, so these are all ways of trying to see sort of inside the product. We'll turn that music down now because it's quite annoying. So the ultrasonic test, you've probably heard of ultrasound when you see it on TV when they're checking out pregnant ladies. It's exactly the same principle. It's the same science behind it. So you use like a certain frequency of sound, which is conducted through the material. It bounces back off certain things and gives you an impression of what's in there. If that's a lady, then you'll see them applying the gel to the belly, and then they'll do the scan, and it'll show up on a screen, and you'll get a sort of cross section of the baby. On this, they're doing the same thing. They're applying like a conductive jelly to help the sound sort of travel through, and then the guy will start to scan it with his little ultrasound thing there, and this graph is sort of picking it up, and he'll sort of be able to tell whether or not this it's bouncing back off a hole or a fault. Okay. Scoot this along now to magnetic particle testing. So what you do here is this only works on sort of metal items. So you attach the item to a magnet and then you literally spray it with iron filings. Okay, so the magnet will attract those iron filings to it. You turn it off, shake all the iron filings off, or so you think, But what you'll actually find is that some of the iron filings will stay inside little microscopic cracks, and these can show up under UV light. If you've got a part that is not metal, then you can use a special liquid. So you can dunk it in the liquid, you rinse it all off so you think everything's okay, and then you shine it under a UV light, and hey presto, you can see where some of that liquid has stayed. And these are little cracks that they're invisible to the human eye until you do this with them. Okay, so 3 methods of non-destructive testing there. They don't damage the part in any way. Ultrasonics, magnetic particles, or liquid penetrants. We mentioned X-ray vision, so yeah, you can use X-rays. Danger with X-rays, though, is that they are dangerous. Obviously, they're harmful to humans, so you need to make sure you've got a shield, but they do show up a lot of useful information, okay? But it is a very expensive way of doing it because you need your own sort of X-ray kit. Last thing I just want to look at in terms of testing is this thing called a scleroscope. This is a portable way of testing sort of large items, testing the hardness. What you have is a bit like a pinball machine, right? You lift this up and it drops down, and there's a little diamond tipped hammer inside which hits the material and bounces back, and this device measures how far it bounces back. So if you hit a hard material, it'll bounce quite high. Soft material, it'll hardly bounce at all. Okay, so that's a thing called a scleroscope, which you can use for testing on the go, as it were. The last thing we're just going to look at is product testing. So once you've actually made the product, you need to carry out a range of specific tests to it. The point of these tests is they need to be very scientific. You need to be able to do the same thing time and time again, and do that to the different products to be able to judge them. Okay.
At IKEA, we put our furniture through 3 years of everyday home use in just 1 week.
Have a seat. Have a seat.
We call our quality testing Mobile Facta. Each item has to pass the test before it wears the Mobile Facta label.
Okay, now they don't actually use people for testing these IKEA. If you've been to IKEA recently, they do have on display some of the test rigs which they use to replicate human use. So they try and put it through like a year's worth of use in a week. So they basically have machines set up to do these repetitive actions, you know, opening and closing a door, you know, thousands of times, because you know, over the lifetime of a product it would be opened thousands of times, but they need to be able to figure that out in a week. Crucial to this are the use of jigs, all right, test rigs, to be able to sort of set these things up. So this is one for opening and shutting a dishwasher. But yeah, the key thing is it just needs to be repeatable, it needs to be exact, and it just needs to replicate what would happen over, you know, long periods of use. The last thing I just want to look at are some other tests. In this case, we're going to look at Snell tests. So even when British standards aren't enough, and we say British standards are like some of the best standards in the world, for something as serious as a motorcycle helmet, you have these things called Snell standards. And Snell standards are above and beyond British standards. They're very specific to helmets and helmet safety. So you can see these guys here doing a range of tests. They're doing impact tests with different things, you know, different shaped items that are doing the impact. You'll see in a second where they're doing an impact test on a bit of material that's been in the freezer for a week. Because you know, you're going to be wearing your helmet in all kinds of weather conditions, so it's important to see how a material, the product reacts when it's been in the cold for a long time. Okay, so, and again, you can get that for different products, you know, so it might be that for televisions there might be some other more serious sort of products, but the Snell standard is something that you look for specifically on helmets. So your assignment then, okay, so hopefully you've been keeping your little class notes up to date. The last thing I need to do just to see whether or not this stuff has stuck is I want you to describe 3 tests that you could do to a product. I know on here it says the mock challenge. You haven't done the mock challenge yet, but on your assignment there's that picture of the stool stroke bin design that we developed weeks ago. So I want you to describe 3 tests that you could carry out on that product, that seat stroke bin. To help you though, what I want you to do is to break it down into 4 areas. So give me a name for the test, even if it's like a hardness test, yeah? And then tell me what that would actually involve. So how would you test that product for hardness? To be honest, you wouldn't test the whole product for hardness, but you might test a specific material. Okay, hint, hint. Also, tell me why that particular test would be useful. For example, there's no point doing a hardness test on the foam. That's not going to prove anything, yeah? Or it'll just show that you don't understand what testing is. And last of all, how well do you think that product would actually perform? And this is something that I have seen appear on exams before, okay, where the product that you end up designing, it would ask you to describe the tests that you would do and why you'd use those particular tests, okay? So you might say that you might do a particular, you might do like a repeated sit-down test. The test would involve, and you might describe a particular test rig that would replicate somebody sitting down and getting up, yeah, that would run for weeks, 1,000 times doing it. Why that would be useful, because it could test out the wear and tear and how well the material could perhaps withstand stuff, and how well do you think it would perform. So based on that image, you need to be able to sort of make some sort of decision as to how successful it would actually do. Okay? As always, please try and hand that in tomorrow. You'll probably get plenty of time today to get that done in this lesson. All right, this video only takes about half an hour. If you've been doing the notes at the same time, that gives you at least half an hour to get this assignment done during this double. Okay, so please use that time and just get it done, and then you'll have no homework to do. Okay. And that's it. If you want to know a little bit more about testing, you can go to these sites here. The BSI education site is brilliant and breaks it down very well, very appropriately for students. There's more information about the kite mark. If you've got access to iTunes U, there's an excellent video on consumer product testing, which shows you all the various sort of test rigs that can be used. And of course, there's YouTube. You can either look on our channel, but there are some quite good testing videos on the NASA Connect channel. Okay, so thanks for listening. Get on with that assignment, please. And that's it for today. Thank you very much.